me blowing through this problem does nothing unless you guys have made a real solid attempt. Even if that attempt has been terrible. If you make a solid attempt, at least you now understand what you should be listening to. Second, there's a variety of ways to go about this problem. And so every class period I've kind of done it a little bit different because you don't have to attack this just one way. I tend to recognize right off the top that energy is the right way to go, but it really isn't. In this case, energy ends up being the longer way to go. And you'll see that in just a few minutes. So I'm going to start with energy because that's what most of the people in the room did, except for like 3. Is there anybody in here who doesn't understand that this problem can be solved with energy? You know, like somebody would raise their hand to admit that. Do you see a change in height? Seems like a good place to start. That's why, I'm going to start there. And I'm going to make it a little bit smaller because we don't actually need to see all those details now. So when it's at the top of the ramp, what are you thinking? What kind of energy would be there? Well, that sounded like a big mumble. That sounded less of a mumble. Okay. So that kind of energy. When it makes it to the bottom, what kind of energy will we have then? Yeah, we will. So there'll be 2 kinds of kinetic energy. All right, so this seems like a reasonable place to start. And if you got here, well, it's not very far, clearly, but it's a place to start. If you're trying to find velocity, energy is a good place to start. So let's whittle away at this. We want this right here. That's what we want. You can't solve for what we've got here. We do have things that will fill this in. We know the mass, 0.5. You probably have a number for G. But that's it. So we need to find other ways to deal with what's here. And so for you guys who get stumped like really quick, your notes are great in that they show a picture. You know what your notes don't tell you? Any of the steps that we did. So if you couldn't go on from here, then following along still isn't going to help. What you need is to write a note. You need to write down the things I'm about to say. Like, for example, I know that this problem has rotation in it, which is why it was pretty clear I was going to have 2 forms of kinetic energy. If an object's spinning, that's a good place to assume to start. But we can't end here. We have to try and get all of the things into the problem that are going to contribute. For example, it's rolling, and I say the word disk in the problem. That needs to be assigned to you. If I tell you the shape of the object, you should probably recognize you're going to have to replace the moment of inertia with something particular to the shape of this object. So that's not an accident. That's design. You have to put in the moment of inertia of the disk. Now, I could stop there at that substitution, but that doesn't solve my problem. It makes my problem a little easier now because I'm noticing I replaced something I didn't know with something I do know. I know the mass and I know the radius. I could now get closer to solving, but I still have things I don't know. I don't know omega, and I don't know h. So I still have to look for ways of finding more info. I could cancel the m's out right now if I wanted. But it is a rotation problem. And so the next thing I've been trying to tell you guys to look for are words like roll. They say roll, they mean specifically rolls without slipping. That means I can replace omega with something that has to do with the center of mass. These are not incidental things I'm talking about. These are the crux of the problem. This is what makes the problem work. So your next substitution, your very next substitution, should be to replace omega and get everything in terms of the center of mass. Now, we're closer, and I'm beginning to notice things. And as you write notes, one of the things you should begin to notice is I can combine terms. I've got things that will cancel out here. Right? The R's are going to cancel out. But this problem had a small little wrinkle in it, and that I didn't give you the height. I gave you the length of the ramp. It shouldn't be hard to look for the triangle in that problem. 25 degrees. I'm giving you a way to get that height. And no, I'm not going to do all the work for it. You can do the work for it. It's trig. Now I'm at a place where I see that I've gotten rid of all of the unknowns and everything's in terms of just V. I can cancel out all them M's. They're gone. Cancel out the R's. They're gone. And now it's algebra, and it just became completely uninteresting, and I really don't want to finish. Because the moment it's algebra, and I want to tap out. I use 10 for G, which is what got me 3.35 meters per second. This part, don't take it the wrong way. But what I want you to see is this is very formulaic. This process can occur anytime something's rolling. I didn't give anything new. It's not like it was rolling up the hill or doing something bizarre or had a slope or had to go through a loop or anything like that. That's coming. This is just the basics. Now, what you do next, that really is on you. There's a number of ways to go from here. And on Friday, I would have said, jump right to forces. That's probably where to go. But you don't have to. If you solved it this way, well, you should probably be able to reason out that if the ramp is constant, and it is, then there might be a way to get the acceleration just from these variables without dealing with force at all. It's possible. I'm not sure that you know that you'll need the acceleration to get the force. But if anybody remembers anything about November, we often had to get the acceleration in order to get a force. That was pretty common. So it would be no different here. I just have a method of getting the acceleration. It doesn't involve me having to get a net force equation out there. Now, I'm going to do the force part because I also want you to see that you didn't have to do any of this energy stuff if you didn't want to. There's another way to do this problem. But at this point, this is all we can do. If you want to figure out the size of the frictional force, we're going to have to look at force now. So let's look at force now. Move that over here. I don't want to zoom in and do all the force stuff again. We did that on Friday pretty thoroughly. However, this class, did we do the pivot about the center or did we pivot about the point on the edge? We did them both very fast. Okay. There's a reason why you might want to do one versus the other. So let me start by reminding you that mg sine theta minus friction equals ma. I see no reason why I can't just write that down there without having to draw a lot of arrows and stuff. This is net force in the x direction. Do I need to do any more than that for you guys? Okay, but I do want to remember that there's a force this way. There, like so. There's a force this way, like so. And there's a force this way. Right? Now, depending on where you decide to make your pivot point, that really narrows down what happens here. If we make our pivot point here, there's good and bad to doing that. I want to show you both real quick, and I want to take my time. So let's make the pivot point here. We did this on Friday. There's First, only one torque if the pivot point is here. Because the frictional force, it's acting at the pivot point, so that's no torque. And the normal force is acting at the pivot point, so that's no torque. But the weight isn't. The weight is acting a distance r away from the pivot point. So I could, maybe, where'd everything else go? There it is. So I could go back over here and just say, well, this is going to be pivot at edge. Remember, torque has three parts. So my torque would be radius of the disc. The force would be mg. And the angle, well, do we see that the angle would be right there? It'd be that same angle as the ramp. So and that would have to equal I alpha, but here's where this one gets weird. I can't just put I here. I'm at the edge of a disk. So I would have to recognize that I'd have to use the parallel axis theorem. Be the only way to do it. Now, there's an advantage and a disadvantage here. The advantage is that if you look closely, there's lots of things that are very likely to cancel out in short order. First, r mg sine 25 equals, inside here is going to be 1/2 mr squared plus mr squared. Parallel axis theorem. In addition, alpha becomes a over r. You might not see it, but I'm noticing that if you do these things, r cancels out. And it will every time. So I add 1/2 mr squared to mr squared, and that gives me 3/2 mr squared. And I know you're saying to yourself, but Mr. Shelton, you gave us r. Can't we plug it in? You can. Wrong with that, but you probably would have forgotten to convert it to meters anyways. I'm also noticing that m cancels out. Now, this will give me the acceleration. Unfortunately, we didn't want the acceleration. We want the force. But I'll remind you that we often have to get the acceleration to get the force. This gave us the acceleration. I'm looking and I'm noticing if I wanted the frictional force, probably I'd have to do some substitution here in order to get the frictional force. I can see no other way to do it. Actually, there might be another way to do it. First, if you solve this for A, you get 2.8 meters per second squared. Just throw that down there at the bottom real quick. That's the number part. What if, instead, we go ahead and use the center as our pivot point? If we use the center as our pivot point, if you look closely at that picture, if you use the center as your pivot point, that means this will be the pivot point. The weight doesn't cause a torque about the pivot. The normal force doesn't cause a torque about the pivot because it's pointed right at the pivot. The only thing that would actually cause a torque about the pivot would be the frictional force. So if you're wondering why I would want to do that? Well, it comes down to I want to solve for friction. That's the whole goal here. So if I choose to do the pivot at center, well, then my net torque is going to be a little different. The torque arm length is still going to be R. The force is going to be friction. And the angle is going to be 90 degrees. Has to be. And that's going to be I alpha. Well, just a couple of substitutions later, and I know it's a lot of substitutions, but are you noticing it's the same substitutions every time? I need you guys to not just notice that, but to do that. And look, we replaced I with our shape, and we replaced alpha with something that will give us the linear value. But here's the rub. R's cancel out again. And what we get is a pretty simple expression for the frictional force. You see, you might find that if you want a specific force, choosing the right pivot point might make it appear easier. So if you choose a pivot point that's on the frictional force, you can't solve for the frictional force with that pivot. But if you choose a pivot point that's away from the frictional force, you might be able to. So the pivot point is a choice. You can solve the problem either way, but you might be able to get at what you're looking for faster if you're more careful about the pivot you choose. Either way, you just substitute it in. You have to put in the mass, 0.5, put in the acceleration, 2.8, and you'll find the frictional force is 0.7 newtons. I have more to go here, but do you have any questions about what we've done here? All right, a couple of things you should be looking at. First, we didn't have to do any of the energy stuff if we didn't want to. We solved for the acceleration using Newton's laws. And we had the initial velocity as 0. We had the displacement as 2 meters. We could have found the velocity. I'm not saying that that was easier, but it might have been easier. If you knew you're going to have to solve for force, maybe finding the velocity is something that you can get from force faster than energy. There's no reason we had to do both of these methods. I asked the question in an order I knew would make you do more work. Now, not all of you fell for it, but some of you did. Do you think the AP exam writers will do that? Guaranteed. That doesn't mean you will have time to figure out the best, most optimistic order to do things. But be looking for it. As we practice from this point forwards, be looking for it. Also, did anybody check to see if we have enough friction? I didn't bring that up because I wouldn't expect it at this level. I will expect it next week, though, because I gave you the coefficient of friction. We might not have enough. You should see first, because I think they'll do that on FRQ. You think you're all happy and you found this value out, and then you find out you don't have enough friction. And I'm not asking for a lot, but I am remembering that you will have to do all of that and have your calculator in degrees. Makes a difference. And if you work all this out, I'll spare you the trouble. I believe it comes out to 1.8 newtons. That friction is less than or equal to 1.8 newtons, which means you do have enough. This is what's required. This is what you have to work with. You're okay. What should also be something you think about putting in your notes is this is all predicated on having a disk. What if the follow-up question now is, if you replace the disk for an equal mass ring, would that change how much friction is required? Yes or no? Or would it require more friction, less friction, or the same amount of friction? I think students will screw that checkbox up because I think they will think, well, it's the same coefficient, same angle of the ramp, same mass object, so probably same amount of friction. And you'd be wrong. The friction is used differently. What determined the amount of friction wasn't the coefficient, and it wasn't the surface. The thing that determined how much friction was necessary was how difficult it was to turn the object. An object that is more difficult to turn is probably going to need more force to get it to turn. And it is friction that's causing this thing to turn. If you redo this problem and you replace the moment of inertia for the disk with something bigger like a ring, you will find the frictional force changes. I can prove it. It's right here. If I is bigger, it's probably going to require more friction. It's also going to change the acceleration. If I is bigger, you're going to have less acceleration because it's more difficult to turn. You will find the frictional force also changes depending on your objects. Objects that are easier to turn will take less friction. Objects that are more difficult to turn will take more friction. And something else we didn't talk about, and as you guys are taking notes, I hope you're actually taking notes. Like that little tidbit, that's how I can probably get through a multiple choice question faster than you. Right, the last test, I proved a couple multiple choice questions that I didn't have to prove because I just knew that had to be the one that was less or more. You could know that too. And it's a simple idea. It's inertia. Things with more inertia will take more force. So that's straightforward. But I want to throw something else out there. We've got a lot of work in this problem, right? A lot of things done here. Would you agree that the object had a change in rotational kinetic energy? And would you also agree that the object had a change in translational kinetic energy? Both of these mean that work was done. The difference is this network was done by torque, and this network was done by force. There was an unbalanced force that caused a change in the translational kinetic energy, and there was an unbalanced torque that caused a change in the rotational kinetic energy. There is probably a work energy formula for torque. I think you could probably figure it out if you just looked at like how symmetrical these things are. If force times distance is work, what do you think the same version is for torque? I mean, I'm just gonna let that hang there. You should find it out. We've looked at a lot of parallels. And if you don't like that, just go into the chapter. It's in the chapter. You could probably read all about it. All right, the bell rings in 1 minute.